In this last section of our course, we're going to talk some more about numerical integration. This is for when we want the value of a definite integral, but it is difficult or impossible to find an antiderivative. We already saw one technique, the midpoint rule. But let's just go ahead and review this one. In the midpoint rule, we took the idea of the area and we divided it up into rectangles. So let's say we have some function y equals f of x. We're going between some x values a and b. We wanted to approximate the integral from a to b of our function, which is represented by this area. At least with the positive function here, like we have, it doesn't go negative. But we divided our interval up into equal width subintervals. And then we took the midpoints of all those subintervals as the x value that we put into the function to get our heights. Just trying to draw this kind of quickly is a little difficult. And let's say here. So we added up all those rectangles, and those rectangles have a width of delta x is equal to b minus a over n, where n is the number of rectangles. And our formula was that we get delta x times the sum of the function values at those midpoints. So we just have an x sub I guess, 1 through x sub n. And those are all the midpoints of all our subintervals. Today we're going to look at two other very similar ideas to this. First up is the trapezoidal rule. Whereas the name kind of suggests, we're going to be using trapezoids instead of rectangles. Remember, a trapezoid is a quadrilateral, or four-sided shape, where two of the sides are parallel to each other. But the other two sides are not necessarily parallel. The area of such a thing, because we're going to be needing it later, if we have the distance between the two parallel lines is what we usually refer to as the height. We'll call it h. And then we have two bases. We have a base 1 and a base 2. Those are the two that are parallel to each other. And the area of this thing is 1/2 height times the sum of the bases. Really, you can kind of think of this as the height times the average of the bases. The 1/2 of the sum being the average of those two bases. Just like with the midpoint rule, if we start off with our function, so from a to b, we're going to divide our interval up into subintervals. But we're going to use equal widths again. So we're going to have delta x is equal to b minus a over n, where n is the number of trapezoids that we're going to be using. We're going to have all these endpoints of our subintervals. You can say x naught is going to be a. x1 is going to be this next one. That's actually just going to be a plus a delta x, actually. So a plus delta x if you want. x2 would be, well, we're going a delta x further, so a plus 2 delta x's. and so on and so forth, until we get to x to the n, where after we add n copies of delta x, we get all the way to b. So usually we'll go ahead and write out what those endpoints are, but we don't necessarily have to write these formulas if it's easy enough to find out from our picture. We'll see how that goes when we get to an example. Oops. So we'll go ahead and kind of turn this into trapezoids. The parallel lines, unlike what I've drawn from our trapezoid up here, the parallel lines are going to be the vertical lines. We're just not going to use a horizontal line for the top like we did for our rectangles. Say for here, for this part, we're just going to take these two endpoints and draw the line between them. We're going to take these two endpoints and draw the line between them. And we just go along as we go. Some of them might even turn out to be rectangles, but we're not too concerned about that. So it looks pretty good, actually. But what is the actual formula for our trapezoids? Well, let's just say the area of the first one. Let's start with that. We'll write down some of those. The height, well, like I said, the parallel lines are now vertical lines, so our height is actually horizontal, you could say. The heights are always these delta x's. This is the width of these sections we've made. So we're going to take 1/2 times that height times the sum of the two bases. The two bases now, let's say this is f of a, is the length of this parallel of this line here, and then the line parallel to it over here is f of this first one. So I'm going to write this as f of x0 plus f of x1. That's the area of the first trapezoid. The area of the second trapezoid, well, all we've really done here, we have the same base, well, we have the same height. Let's say it that way, because I want to be consistent with the drawing up here. We have the same height, but now we're using two different bases. We're using the function value at x1 and the function value at x2. So we're going to have a 1/2 delta x. It's going to stay the same, but now we're going to have f of x1 plus f of x2. So all we're doing is changing which x values we're using. And we're just going to keep going with this. So I'm going to go ahead and put in the last two as well. So the n-1 trapezoid is going to have f of x n-2 plus f x n-1. And the area of the nth one, the last one, is 1/2 delta x f of x n-1 plus f of x n. And we're just going to add all these together. Note that when we do so, the 1/2 delta x factors out really easily. And of all the f of xi's, we end up with two of each. We have an f of x1 here, we have an f of x1 here, we have an f of x2 here. If I were to put in area 3, we'd have an f of x2 there. Same thing here with the f of x n-1 with this f of n-1. The only two that don't is f of x0 and f of xn. Those don't have anything to pair them with to make two of them. So we're going to get the trapezoidal rule. Where the integral from a to b is approximately equal to delta x over 2 times the sum of f of x0 plus twice f of x1 plus twice f of x2, and then so on and so forth until we get to twice of f of x n-1 plus f of x n So notice the pattern here is that we have a 2 on every single function value except for the 2 endpoints. We want to remember that pattern. That's kind of one of the things that makes it different from the midpoint rule. The other thing is that we're not using the midpoints of these intervals. That's actually makes it a little bit easier to do. Instead of having to find all these midpoints and use those, we can just use the endpoints of our subintervals. Let's go ahead and see this in action, though. Let's look at problem 12. Here, we want to approximate the integral from 0 to 4 of 8 over x squared plus 3. And they tell us that we want to use 4 rectangles. So n equals 4. We have the interval from 0 to 4 that we want to split into 4 sub-intervals. Delta x here is b minus a divided by n, or just 1. So our endpoints are just going to... Let's go ahead and actually put out a number line here. We're going from 0 to 4, and we break those at 1, 2, and 3. Those are our endpoints. Easy enough. In the trapezoidal rule, that means that we're just going to approximate this integral, well, approximately equal to, it's not exact. We have a 1/2 times our delta x. Well, our delta x is a 1, so I'm just going to leave a 1/2. We have the function value at 0. What is the function value at 0? We take 0 and we plug it into 8 over x squared plus 3. Well, of course, that just gets rid of the x squared. We're left with an 8 over 3. Now we take twice the function value at 1. So we plug 1 in here. We have 8 over 1 plus 3. That's 8 over 4. But we have to double it. We get a 16 over 4. You could simplify that if you want to. I'm just going to add them together in a calculator in a moment. Now we plug in 2. We have 8 over 4 plus 3. That's 8 over 7. But we need to double as well. We have to follow that pattern for our trapezoidal rule. We plug in 3. 8 over 9 plus 3. So 8 over 12. Again, this is one we need to double. And finally, the last one, we don't need a double. We plug in 4, 8 over 16 plus 3. Used to writing 16. It's 8 still over 19. And like I said, plug that into a calculator. We get approximately 5.35338. Just rounding it a little bit. So actually, I probably use more digits than are exact. So relatively easy to do, at least as long as you don't have too many endpoints. In general, if you're going to be using a really big n, it's probably you're using a computer to do it for you. But at least a small n can be done by hand fairly simply. The other rule is what was known as Simpson's rule. Of course, the name here doesn't suggest what we're going to do like it did for the trapezoidal rule. But the idea here is that when we use the midpoint rule, we use areas under horizontal lines to get rectangles. Those are basically degree 0 polynomials. When we did the trapezoidal rule, we instead used areas under more general lines. We didn't require it to be horizontal at the top, and so we basically used degree 1 polynomials. Simpson's rule instead uses degree 2 polynomials. We're finding the area under parabolas. We're going to essentially approximate our function by a bunch of parabolas and turn that into a formula for an approximation for the area. it turns out if we have 3 points, at least 3 equally spaced points, A, B, and their midpoint M, these are equally spaced, and we have 3 points out in space with those x values, there is a unique parabola. There's only one parabola that can pass through those 3 points. Now, if these were actually horizontal, if these actually were linear points, if these were all on the same line, there's actually not a parabola that passes through them, and instead we have a line that passes through them. But in the more generality, it's a parabola fits through 3 points. The area under this parabola, so if we were to draw in the area here, the area, let's say this is we can call that p of x for polynomial. The area from a to b of this underneath this polynomial is actually can be found using the fundamental theorem of calculus, and we can actually write it in terms of the values, the y values, at these 3 points. And I'm not going to derive this or derive what that quadratic actually is. Just kind of take my word for it. It's not too difficult, but I don't want to spend time on it. It's actually equal to b minus a over 6 times the value of p at a plus 4 times the value at m plus the value at b. So the values at the 2 endpoints added to 4 times the value at m times a factor here. So when we do this with a more general function, approximate a more general function, say we have our function y equals f of x. We go from a to b. Okay. We're going to divide up our interval into subintervals. We're going to use n of them. However, here we do have to be a little bit careful for how we're going to do this. We need to choose an even n, and that is very important. It mostly comes down to the fact that we need, in order to work with the parabola, we need 3 points, and that means that we're going to essentially pair up the points in here. Or really, we're taking triples, but there's going to be repeated ends of those. We're going to have our endpoints of our subintervals. Of course, x0 is again going to be a. x1 will be a plus delta x. Of course, delta x is going to be b minus a over n, like it's been in all the other ones. So these are all the same as they were in the trapezoidal rule. But now we're going to be taking these things, and instead of just saying this first part is going to be approximated by some formula, instead we're going to have to take these first 3 points. We take those 3 points, we find some parabola that passes through them, and find the area under that parabola. Then we take the next 3 points. Well, we keep this point as well, so we're repeating that point. I guess that's x2. So x2 gets repeated, and we use this point and those two new points. We find another parabola that passes through those, and we approximate the area that way, and so on and so forth. I don't really have room on this slide, so let's go ahead and move to the next one. So area 1, this is using x0, x1, and x2. This is going to be 1/3 of delta x times, remember we had 1 times f of x of the first point, we have 4 times the middle point, so that's f of x1, and then we have just 1 times the other endpoint. Notice here that we have a 1/3 instead of the 1/6 that we had back here, because remember, this is from A to B. We're going from A to x2 for this part. That's not just a width of delta x. That's a width of 2 delta x. And so, really, this b minus a on top is going to be a 2 delta x. So 1/6 become a 1/3. Moving on to the second area, we're using x2, x3, x4. We have a very similar formula. We're just changing which of these we're going to have in here. We're going to have f of x2 plus 4 times f of x3 plus f of x4. And we could continue with this. Just keeps going. Then we add all these together, and we get an approximation for our area. Of course, all these 1/3 of delta x are going to factor out. So we have a delta x over 3 out in front. Inside, well, notice that we do get to keep f of x0 just by itself. It doesn't really pair with anything. In fact, the f of x1 doesn't pair with anything either, but it has a factor of 4, so we need to keep that. F of x2 is repeated. It appears twice. It only has a 1 here, but it also appears here. So we get a 2 on that one. x3 only appears once, but it has a 4. x4 appears here, and it would appear in the area 3 as well, so that gets doubled. And so on and so forth, until we get to the end. So the f of x in minus 2 is going to be the first endpoint of the last parabola. It's going to be doubled because it will combine with the previous parabola. F of x in minus 1, that's going to be the midpoint of the last parabola, but it's going to have a 4. And then finally, f of x in, it's an endpoint of the last parabola, but it doesn't have anything to pair with, so it doesn't get doubled. So kind of a very similar formula as we got with the trapezoidal rule. The two things to note here is, first of all, instead of dividing by 2, we divide by 3 out in front. And instead of having a pattern of 1, 2, 2, 2, 2, 2 until we get to 1, we have 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2. So let's even go ahead and just write that out. I'll just abbreviate it like that. So notice here that because we've chosen an even number of subintervals, this pattern will work. It doesn't actually. If we chose an odd number, then we'd end up with like a 2, 1 at the end, and technically it wouldn't even work with the parabolas. So it is very important that you choose an even number of subintervals, and you don't really have to think about what parabolas we're using here. It's just a matter of following the pattern. So let's go ahead and use this in the problem 12 that we already looked at. So remember here, we were approximating 0 to 4 of 8 over x squared plus 3 with n equals 4. They specifically chose n equals 4 because they wanted to use Simpson's rule here, and you need that even number. We had a delta x is 1, and we had our endpoints. That's 0. We had endpoints at 1, 2, and 3. So this integral is going to be approximately equal to delta x, which is 1, divided by 3, times a sum. And we're going to use the same y values that we did before. When we put in 0, we had a y value of 8/3. When we put in 1, we had a y value of 8/4. Except this time we're going to be multiplying by 4. So 8 times 4 gives us a 32/4. When we plugged in 2, we got 8/7. This time it's going to be multiplied by 2. So we follow that pattern, 1, 4, 2. So we have a 16/7. Next one is a 4. When we plugged in 3, we got 8/12. So this time we get a 32/12. Finally, when we plugged in 4, we got an 8/19. So essentially, this is going to be exactly what we had back here, except instead of a 1/2, we have a 1/3, and well, actually, the first, third, and fifth terms here are exactly the same. The second and fourth ones are now multiplied by 4 instead of multiplied by 2. Putting that into a calculator, we get an approximate value of 5.3467. And how good of an approximation that is, I'm not really sure. We could find it, but it doesn't really matter too much. The point is how do you follow this rule? Now there is a little bit more to talk about when it comes to these rules. I'm going to go ahead and put those in another video. So just to make sure this one doesn't run on too long, just kind of split it up a little bit. So I'll see you guys in that one.